This industrial case study explores the topic of smart energy meters within the framework of the European project titled Personalized Education in Measurement Science and Technology Empowered by Machine Learning. Let's look at a scenario where we enhance renewable energy performance. As you can see in the graph, we have an electrical network connecting several houses. Each house is not just a consumer but also a producer, equipped with its own solar panels. Imagine these houses are part of a community where they can share surplus energy with one another. Our goal here is to schedule power consumption in a way that reduces reliance on the main grid and maximizes the use of this shared green energy. However, this is only possible with precise data. We need accurate measurements of grid purchases, home consumption, and solar production. All this data must be sent to a server and processed effectively to optimize the schedule and meet our energy goals. Now, let's shift our focus to another scenario. Imagine a standard household with typical appliances, a dishwasher, a TV, a PC, and other common loads. At the end of the month, the homeowner pays a bill based on exactly how much energy those appliances consumed. But here is the catch. We can only trust that bill if the energy meter is measuring the consumption perfectly. Accuracy is vital for both sides. The consumer needs to know, is this bill fair or am I being overcharged? At the same time, the supplier needs to know, is the meter working correctly so I can bill for the actual energy provided? This scenario also emphasizes the fact that accurate energy measurement is important for both consumers and suppliers. Accurate energy metering extends far beyond simple billing and load scheduling. It is a critical component for renewable energy integration, grid state estimation, and supply-demand management. Consequently, revenue metering is strictly governed by the legal metrology framework. This framework mandates that all devices used for energy measurement must be verified by an accredited body. Furthermore, any legal disputes arising between consumers and suppliers regarding measurement accuracy must be adjudicated within this established regulatory structure. Now let's look briefly at how legal disputes are handled in this framework. We will refer to the consumer as the weaker party and the supplier as the dominant party. First, imagine the consumer suspects an error. They can file for an intervention to have the meter verified. If the meter turns out to be faulty, the supplier pays the service fees and settles the difference. However, if the meter is working correctly, the consumer was mistaken and must pay the service fees themselves. On the other hand, if the supplier suspects an error, they can request a check immediately without starting a formal dispute. If they are right and the meter is faulty, they then open a dispute, pay the fees, and settle the bill. If the meter is fine, the supplier simply covers the cost of the check, and business continues as usual. Over the years, the electrical grid management sector has witnessed significant advancements in metering technology. The pinnacle of this evolution is the smart meter. A smart meter is a digital device designed to measure and record the consumption of utilities such as electricity, gas, or water in real time. Unlike traditional meters, it transmits this data remotely to the utility company. These devices continuously monitor consumption, store data internally, and transmit it across the network. Furthermore, the latest generation of smart meters features two-way communication, allowing not only for data measurement, but also for the reception of remote commands. So what are the actual benefits of using smart meters? Let's break this down into two groups, the consumers and the DSOs. On the consumer side, the primary benefit is trust. As we will discuss shortly, consumers can use data analysis to verify that their bills are accurate. Beyond that, they gain real-time visibility into their usage. This allows them to schedule their heavy loads more efficiently, save energy, and take advantage of flexible, multi-tariff pricing structures. On the DSO side, the benefits are equally powerful. Smart meters ensure accurate billing from the supplier end, but they also act as sensors for the grid. They allow operators to detect outages faster, manage grid stability in real time, and significantly improve their ability to detect power theft and anomalies. The benefits previously discussed can only be realized through the deployment of advanced metering infrastructure, AMI. AMI is not merely a single device, but an integrated ecosystem comprising hardware, software, communication networks, consumer energy displays, and customer management systems. Currently, government agencies and utility providers are prioritizing AMI as a cornerstone of broader smart grid initiatives. This shift occurs because AMI represents a significant evolution beyond traditional automatic meter reading (AMR). Unlike its predecessors, AMI enables two-way communication, facilitating real-time, time-based pricing, and dynamic demand response actions. Turning our attention now to the infrastructure that makes this all possible, the communication layer. In the latest advancements of smart energy meters, the communication architecture is effectively the nervous system. This is because, without a reliable, secure, and real-time link to the central system, a smart meter is simply a digital logger. However, establishing this link is the primary engineering challenge due to the fact that energy meters are deployed in diverse operating environments, from deep urban basements to rural, poorly serviced locations where connectivity is naturally unstable. To solve this, first, there is the Powerline Communication, PLC. This is often the primary choice because it leverages our existing asset, the power lines themselves, operating specifically within CENELEC bands A and C to avoid interference. Where power lines are too noisy or impractical, the cellular networks come into play. Depending on the technology, these networks can range from traditional GPRS to low-power wide area network technologies like nitrogen monoboride-IoT and LTEM. For areas requiring high redundancy, wireless mesh networks are used, using protocols like YBRI or YSUN. This allows meters to act as repeater nodes, creating a self-healing web. Perhaps the most robust development is the hybrid PLC-RF approach, seen in standards like Prime and G3 PLC. This provides a failsafe. If the power line carries too much noise, the meter automatically switches to radio frequency to ensure the packet is delivered. And finally, we must not forget the Home Area Network, HAN. This is the consumer-facing side, using short-range protocols to connect the meter to in-home displays, bringing the data directly to the user. When we look at the server side of AMI, we can break the infrastructure down into three main layers. First, we have the Data Concentrator Unit, or DCU, which collects data locally. Next is the Head-End System, or HES, which acts as the communication gateway. Finally, sitting at the top level is the Meter Data Management System, or MDMS. This is the core system responsible for storing, validating, and analyzing all the massive amounts of data coming in from the grid. Let's have a closer look at each of these layers. By definition, the DCU serves as a local aggregation point within the advanced metering infrastructure. Its role is to consolidate data from a specific cluster of smart meters. The DCU operates as a gateway. It takes the aggregated data collected from these local meters and securely transmits it upstream to the central server, known as the Head-End System, or HES. The deployment of DCUs provides three key operational benefits to the grid. Network optimization. It significantly reduces the communication load on the wider network by processing data locally before transmission. Connectivity mitigation. It addresses connectivity challenges in difficult environments. Intermediary role. It acts as a stable, intermediary link between edge devices and the central head-end system. Finally, to ensure interoperability across the network, the DCU supports standard industry protocols, specifically IEC 62056 and DLMS-COSEM. Proceeding to the central component of the server infrastructure, we have the Head-End System, or HES. Fundamentally, the HES serves as the central communication hub for the entire smart metering infrastructure. It is the focal point where all upstream field data converges. Its primary functions are twofold. First, it is responsible for collecting, validating, and managing data received from both the data concentrator units, DCUs, and the individual smart meters. Second, it establishes the necessary two-way communication channel with the utility's back-end servers. In terms of operational capabilities, the HES provides critical remote management features. It allows operators to perform meter configurations and firmware updates remotely over the network. Additionally, it supports real-time data retrieval while strictly ensuring data integrity and security throughout the transmission process. Finally, the MDMS is defined as the core software platform responsible for the large-scale storage and processing of all incoming meter data. It acts as the central repository where raw data is transformed into actionable intelligence. This system performs three critical operational functions. It executes validation, estimation, and editing (VEE) to ensure data quality and handle missing values. It handles billing preparation and load analysis. It runs advanced algorithms for anomaly and fraud detection. Critically, the MDMS integrates seamlessly with other utility systems, including billing platforms, customer relationship management, CRM systems, and demand response modules. Ultimately, the goal of the MDMS is to enable efficient, data-driven energy management across the entire utility enterprise. Despite their operational advantages, smart energy meters introduce several significant risks and concerns. The most critical vulnerability stems from bidirectional communication. By exposing the power grid to external networks, these interfaces create potential vectors for cyber attacks, which could result in power outages, data theft, and non-technical losses. To mitigate this, adherence to the IEC 62056 standard is essential as it enforces strict encryption and authentication protocols. Concerns regarding radio frequency, RF exposure, are frequently cited. However, the typical strength and density of the RF signals used in smart energy meters generally falls below FCC hazardous limits. However, an indirect operational risk is remote disconnection. In dispute scenarios, suppliers can remotely cut power, potentially endangering vulnerable individuals who rely on heating or life-sustaining medical equipment. Additionally, historical data, 2012 to 2014, indicates past issues with fire safety, which have since prompted hardware patches and stricter deployment protocols. Last but not least, the high granularity of data transmission poses a significant privacy challenge. Without safeguards, this data can reveal sensitive household behavioral patterns and daily routines. To prevent misuse, systems should implement dynamic reporting intervals and multi-layered data protection mechanisms. As previously discussed, energy meters operate within the strict framework of legal metrology, which mandates the metrological verification of all revenue metering devices. To illustrate the scale of this requirement, consider the Italian market alone, where over 13 million power meters are currently operational. Conducting standard metrological verification for every individual unit is an intensely time-consuming and resource-intensive process, making it systemically inefficient. However, this verification remains critical. As noted earlier, anomalous meters pose a significant risk of financial burden to both consumers and distributors. With the advancements of smart energy metering, it is now possible to implement data-driven anomaly detection through extended observation. The hypothesis is to assume that an energy meter begins its life cycle functioning within admissible metrological limits. However, over time, performance may degrade, causing the device to deviate from its nominal accuracy specifications. By extracting the characteristic features of the energy measurement time series during the meter's known, healthy state, we can establish a baseline. Continuous monitoring against this baseline allows us to detect when the meter begins to drift from its nominal specifications, enabling remote identification of potential faults. Of course, this kind of extended observation requires a sophisticated system for data collection. To make this reality, the system needs to meet several key criteria. First, we need metrological traceability, which is guaranteed by using verified smart meters right from the start of their life cycle. Second is computational efficiency. This is achieved by using lightweight, data-driven methods like supervised learning within the machine learning terminology. For security and accessibility, it is possible to rely on modern cloud infrastructures based on the Industrial Internet of Things, IIoT. And finally, to ensure interpretability, user-friendly graphical interfaces can be implemented to ensure operators can easily interpret the data. If done properly, the process starts with the smart meter sending power measurements through an IoT gateway directly to the cloud. Once the data is communicated, the cloud infrastructure can provide three key capabilities. First, the database, which is crucial because it builds the ground truth to train any supervised machine learning model. Secondly, the visualizer services can provide clear insights into consumption patterns and load profiles for individual houses or factories. And finally, the anomaly detection algorithms. can not only spot errors in real time, but can also predict when a meter is reaching the end of its useful life. Thank you for your attention. This video was produced through the collaboration of SS Cyril and Methodius University of Skopje, the University of Niš and Politecnico di Milano, within the framework of the European project, Personalized Education in Measurement Science and Technology Empowered by Machine Learning. More information about the project can be found on the project website and LinkedIn page.